Welcome to TechBite number 3. Today, Adnan is going to be introducing a detector technology that is changing the game in optical gas sensing. Can you tell us what technology you're going to be talking about?
Sure, I think it's a really exciting and disruptive one. It's a detector technology that works within the mid-infrared zone. So when we're talking about applications like environmental monitoring, for example, automotive pollution detection, where on the roadside you might have a system that's monitoring exhaust gases like SO2, or industrial process control, where a manufacturer wants to get feedback on the levels of, I don't know, NO or ammonia exhaust from their chemical processes and adjust the additives, or medical breath analysis, monitoring oxygen or CO2 levels in a patient. These are all common in the sense that the core optical gas sensing technology is working within this mid-infrared zone, what we call the fingerprint zone. And this is where this really exciting new detector technology comes in.
Does this technology have a name?
It does, though I should give you some background first. It's based on a semiconductor material called InAsSb, indium arsenide antimonide. This is a lot tougher to grow than silicon or InGaAs, but it has brilliant sensitivity between 2 and 10 microns and even further. So the name of our detector is called multi-stage InAsSb.
I imagine this isn't the only technology that works in this fingerprint zone.
You're right. I mentioned before that this is a disruptive technology, so it's disrupting a number of existing detectors that are being used in the mid-infrared applications already. Things like pyroelectric detectors that are used in cost-effective NDIR applications, or lead salt or mercury cadmium-based photoconductive devices that are used in these really high-precision spectroscopic analysis applications.
But is it really possible to replace such varying technologies with just one type?
In the wavelengths where they overlap, yes. Since it's a solid-state process used to manufacture InAsSb, we can take advantage of the same kind of economies of scale as the world does in producing silicon, producing it very cost-effectively at high numbers. When it comes to high performance, however, the conversation becomes a little bit more tricky and needs some further explanation.
How so?
Well, I should start by explaining D-star, or specific detectivity. This is a very common measure of how performance of these kind of mid-infrared detectors is measured. But one thing that it doesn't take into account is just how much noise is introduced when you build the electronics around the detector itself. And this is really crucial when it comes to our multi-stage InAsSb. The multi-stage part of the name is where the secret is. You'll remember I said that InAsSb is really hard to grow, right? Well, we're able to get around this by growing thousands of tiny cells and connecting them together in series to build up the whole active area. And this has some really amazing impacts on the detector's electrical characteristics. For one, its shunt resistance is really high. So much so that you can get away with amplifying the signal that you get from the detector many multiples of times more than these other detectors. So if you get the electronics right, you can really get a comparable or better performance than these historical technologies.
But won't it be difficult for these different users to work out how to get those electronics right?
That's a good point. It's definitely not a drop-in replacement, and it does need some work that depends very much on the setup of a user's existing system. But we've been helping users transition from their historical technologies for over half a decade now. So actually, I'd like to show you an example of this and just how powerful this InAsSb multi-stage can be.
You have a demonstration for us?
That's right. This is one of our multi-stage InAsSb detectors right here. And on this circuit board are some amplifier stages applying very high gain. In this circumstance, over 1 million gain. So before I show you what it can do, I should explain some basic principles of remote temperature sensing. Every object will give off blackbody radiation. The hotter an object is, the more that light shifts towards the visible and the more light it will emit. This explains why a soldering iron will glow bright red when hot. The cooler an object is, the flatter that radiation curve will become because the less light it will emit. And so if we want to measure the temperature of a cooler object remotely, your sensor needs to be that much more sensitive. So for example, if you wanted to detect something at room temperature, you'd need a really sensitive device, possibly thermoelectrically cooled. But if you see here, I have our little multi-stage InAsSb detector connected to a neat oscilloscope, and the output you can see here on the screen. This detector, with the really high gain that is only possible with this kind of structure, is sensitive enough to detect the blackbody radiation even from my hand.
Are there any other resources that you have to help people looking to change?
We do. Besides the detector itself, which is available in a couple of wavelength ranges in different packaging options, we have cooling options and different active area sizes. We have various loanable modules where the electronics are already set up, and reference diagrams and help notes to get people familiar with this new technology. We also provide a bespoke consulting service where we can help to develop a very specific design that fits even the most niche requirement.